Hey kiddos, so I'm going to do one more quick video on section 5.1, Intro to Soil Systems. We just have three little things to kind of finish up this topic. So we're going to look at porosity, permeability, and pH starting on page 242. We're going to look at, struggling with this book, soil sustainability, and then we're going to work on this to do. So let's begin with this right here. So porosity, permeability, and pH. So these are kind of just three definitions we need to understand and how they apply to sand, clay, and loam, or how they apply to soil in general. So let's start with porosity. This is related to soil's texture. So think of like the feel of it. It is the amount of space between particles. You should remember from our last lesson, whenever we were looking at those three different types, right? Those particles have different sizes. Remember clay being the smallest, then silt, then sand. So because of that, I guess loam or silt. Because of that, remember that that can change the space between those particles. Remember we showed that picture about how clay is very small, so there's not a lot of space between them. But with sand, that's not true, right? Sand could be very large, and that has a lot of space and gap between them, right? Permeability is with what ease gases and liquids can move through that soil. So we've already looked at percolation, which is just liquids moving through it, so water moving through it. Permeability is just kind of like a catch-all, gases and liquids. So solids with a very fine clay particle texture, so we're going to those very small clay particles, have lots of micropores. This results in a combined large pore space made of many microscopic pores but low permeability. So because that clay is so close together, it's not very permeable. This is because water can easily fill these spaces and adhere to the clay, trapping the water film around the clay. That's how something like clay, very small, poor permeability. Sand, on the other hand, you could probably understand this, right? Have fewer macropores and with a small total space. These spaces are too large for water's adhesive properties, that's water sticking to other particles, to work, so sandy soils drain well. You've probably seen, right? Someone walking on the beach, even though the water was just here, that water is going to drain almost instantly through that sand, where in comparison, something like this is the land run, this is the bike race I do every year. That water gets stuck in there. Even if it rained days ago, that water can just kind of stay in there and it doesn't permeate through that very quickly. So it kind of just pools up and stays and gets really gunky. So since that clay that we just looked at, it doesn't have a lot of permeability. This means it can really lock and dissolve minerals, making it hard for plant roots to access it, though. Those minerals are there. They're actually doing a really good job of building in the clay, but it can still have low fertility, meaning the plants really can't access the nutrients, so they're not really going to grow very well, even though those nutrients are there. So clay is not necessarily the best type of soil for growing plants, even though it is very rich in minerals. So we're going to kind of focus on clay some more and get into pH and acidity. So clay soils encourage high acidity. So clay, high nutrients, but low permeability, low fertility, high acidity. The high acidity has some benefits. So as soil absorbs more water, clay particles begin to fill up with positive hydrogen ions. And remember, pH is the measurement of hydrogen ions. So this binds soil more tightly to the clay particles, making the soil even more acidic. It also reduces the amount of other positive ions it can bind. So these hydrogen ions kind of just take up all the space, basically. So the potassium, magnesium, ammonium, those can't really get in there, and they just leach through. Remember, they just drain through. So actually, clay loses a lot of those nutrients just because they can't get trapped in there because the hydrogen's already there. Along with the loss of these important nutrients, as soil pH decreases, a lot of those ions become available to plants. Basically, like they're broken down because whenever that pH lowers, they can access them now. but those are actually toxic to plants. So clay usually isn't actually a very good soil for growing plants. So acidification of soil has had a major impact on forestry in Northern Europe. So this is actually what's going on here has had a huge impact on forest service, or not forest service, like forest and logging companies. This is mainly because there's a lot of acid rain there because of industrial pollution. We learned kind of about that in topic, what was that, 6 or 7? Now the soil is very acidic. This is happening. There's not a lot of nutrients that can be accessed, but then when they try to lower the pH, a lot of these poisonous components come out. This in turn has meant more available aluminum and iron in the soil, causing damage to evergreen forest through needle death. So basically what's happening, industrial pollution, acid rain happens, that lowers the soil pH, that releases these iron and aluminum. Now you're going to have these poisonous things coming into the soil. All right, so now I kind of want to look at soil sustainability. So in this class, we've talked about sustainability a lot, right? A resource, whatever it is, water, land, crops, sunlight, whatever we want to think of, can be sustainably or unsustainably used. So what we need to realize is soil has that same issue. Fertile soil is a non-renewable resource. Remember? So we'll kind of explain why it's non-renewable. A lot of people don't realize that it's not renewable. They think, oh, there's just so much soil out there. There's complete access to it. We can just use it as much as we want. But what you need to realize is that once soil is lost, and we're losing a lot of soil, those videos that I recommended in the first video do a really good job of showing you like how we're losing soil. We're actually being very unsmart with our soil use. So we're actually using it too quickly, losing it, and we can't replenish it. It can't be replaced quickly. So even though it can be replaced, it takes so long that we consider it non-renewable. Same thing with oil, right? Oil takes too long to renew. So in our lifetimes, we're not able to renew it. So it's considered a non-renewable resource. So soil formation takes a very long time. The natural soil renewal rate is about 1 ton per hectare per year. So if you had a hectare of land, which is a unit of land, look at it's a distance, every year you could get about 1 ton of new soil. This is under the best conditions possible. So that's like best case scenario. That's usually in a wet, temperate climate. So this is only about 0.05 to 0.1 millimeters of soil per year. So think about that. In that whole hectare, you might want to Google and see what a hectare looks like. You're only getting about a millimeter of soil. That's not a lot, right? Think of a ruler. This is that first little dash on there. And this is only after the initial chemical and physical weathering has occurred and fine material and soil organisms are present. So what this actually represents is the natural rate at which soil regains their fertility. As a consequence, soil use often exceeds soil formation. So we're using soil much quicker than it can be formed again. So soil should be considered a non-renewable resource. We are already having issues with renewable resources. We'll see this kind of down here. So fertile soil has enough nutrients for healthy plant growth. The main nutrients, these right here, NPK, nitrates, phosphates, and potassium. If you use fertilizers, you put a lot of that in there. And there are many micronutrients that plants need as well. These nutrients can be leached to the soil, so we remember what leaching is, and removed when a crop is harvested. So if we use the soil to grow a crop, as soon as we remove that plant for our use, we've taken that resource out of that system, out of that ecosystem of soil. So once we take it out, that soil has lost all of those nutrients. They have to be replaced in agricultural soils via chemical fertilizers. This is usually why big industrial farms have to use fertilizer, because they've taken all of that out of the soil and there's nothing left for the soil to give. There's ways that we can add these nutrients back. You can use fertilizers. You can grow legumes. Think peanuts. You can have crop rotation, meaning like every year you plant something different in that spot, and maybe you rotate 4 crops over 4 years. Or you can use organic matter, so like maybe manure or compost to add nutrients back into that soil. But if you try to just plant over and over and over again, it wouldn't work. So for this to do, I'm just going to look at this first page. I'm not going to go into this question two. You can if you want to, but really the point that I want to get across happens in these two graphs here. So if we look at this figure here, what we're seeing is graph A right here shows the harvest from one field of crop in the Philippines over 25 years. So it looks like it starts in what, like 1965, goes to 90. This red line is with fertilizers, so we're adding these three fertilizers in PK. The green line is no fertilizer. And it shows the yields fall over this time. So we're kind of like seeing this decrease, right? So this is the yield per hectare. So just think of how much crop we can produce in that land per certain unit of like distance. Graph B here shows the annual yield of cereal crops. Cereal crops, think of like wheat, grain, stuff like that. So it shows the annual yield, how much of those grains per capita is not shows that it's not increasing. So if we look at this, it wants to kind of explain what these graphs tell us about carrying capacity and sustainability. I'm not going to give you all the details on this, but really this graph does a good job of showing this, right? These descriptions kind of tell you world cereal production is unable to keep up population growth. So we can kind of see, as long as you understand what this is, right? Cereal production per capita. Remember what capita is? You can kind of see that we're producing more, but it's not quite able to keep up with our population growth. The population is continuing to grow, but when we look over here, right, even when we're using fertilizers, we are slowly decreasing. If we had a trend line, it'd probably be kind of in here. We are slowly decreasing the amount of crops we can produce, even with fertilizers. So what's kind of scary to me on this is like, without fertilizers, the soil, let's say it's about 5, right? Had a unit of about 5. We've already decreased down from about 8 to 6. So with fertilizers is almost the same amount of production as 25 years ago without fertilizers. So eventually this will probably keep trending down and we'll probably match this eventually. Feel free to work on the other questions below, but again, I'm not going to cover those. That is it for 5.1, and we will start on 5.2 in the next lesson.